Hi, so we go into a new chapter today. I got a new haircut for that, so let's get going. We've already found how to find the area between a function and the x-axis because integrals, definite integrals, find signed area, and signed area is so close to regular area that we could do it. Well, today we're just going to extend that a little bit and find area between curves and straight lines, 2 or 3, 4 of them, that form some type of boundary, and they don't even have to be functions. So, to start off with, say we have y equals f of x, this red curve, and y equals g of x, this green curve, and we're trying to find the area in between the curves, between x equals a and x equals b. So we're trying to find all of this area in here. Well, we can do a similar type thing we did when we first started doing Riemann sums. We can divide a to b up into n sections. And we can call this x sub 0 and this x sub n. And then we're going to have all these other x's in there. So let's just look at the kth section from xk minus 1 to xk. And just pick some value, could be anywhere in there, c sub k, and go up there and make that the height of this rectangle. And the width is going to be x sub k minus x sub k minus 1, which we've called delta x sub k before, so we might as well do it again. And we just go up and make our rectangle at that height. So what is that area? Well, the height is f of c sub k minus g of c sub k. And the width is still going to be delta x sub k, but that's only one of the n rectangles. So what do? We add them up from k equals 1 to n, or as the largest partition size approaches 0. But we still have some error. Look, we have extra up here, and we're missing some down here. So what we do is, the last thing is take the limit as n approaches infinity. And that should find the exact area. Well, the nice thing about it, that's exactly what an infinite Riemann sum looks like. The only difference is, before we just had f of c sub k there, now we have a different function. We have f of x minus g of x that we plugged in c sub k to. That's just another function. So this is really just a definite integral from a to b. Instead of f of x dx, it's going to be f of x minus g of x dx. So that's our formula to find the area between these two curves. And if the x-axis happened to be g of x, we'd have our definite integral that we did before when we were finding area. So let's try a first example. Find the area between this parabola and this upward shaping parabola. 7 minus 2x squared is going to go down, and 4 plus x squared is going to go up. So one thing we are going to have to do now that's different is we're going to have to find out where they intersect. So I'm going to set x squared plus 4 equal to this other downward shaping parabola, and I get 3x squared equals 3, or x equals plus or minus 1. So we can see they intersect here at -1 and at +1. Now, I think it's a really good idea to draw in your rectangle. So I'm going to make that little rectangle, and this width is going to be represented by dx, and I would write it right down, and then we're going to just use this formula. It's the integral from -1 to 1 f of x minus g of x dx. But we have to be careful. We want this to be a positive area, so we have to take the upper minus the lower. The higher up you are, the bigger the y values are. So we're going to want to go black minus red. And the black is 7 minus 2x squared, and the red is x squared plus 4. Notice back here, maybe should have mentioned it at that point, it doesn't really matter. You don't have to be careful whether you're in above or below the x-axis, because when you take this minus a negative number, you're still going to get exactly what the side of this rectangle is. So you don't have to worry about whether you're above or below the x-axis. Okay, so let's finish this off. If I combine these, I get 3 minus 3x squared. And you could just go from -1 to 1, but I think if we know something about parabolas, we can see that it's symmetrical on this side of the y-axis and on this side. So you could just go 2 and just go from 0 to 1. It's just going to make your calculations a little bit easier. So the antiderivative is 3x minus x cubed. When we plug in the numbers, 0 gives us 0, 1 gives us 3 minus 1. 2 times 2 is 4 square units. So in this little region, there's 4 square units. Remember, 1 square unit would be like that. So this isn't drawn completely to scale, but that would be 4 times as big as that if you actually drew it to scale. Okay, so let's try another one. Find the area in the first quadrant. That makes our life easier. We only have to draw one of the 4 quadrants. Below y equals 1. And between y equals x. So y equals x is going to look like that. And then we have this parabola. When x is 0, you get 0. When x is 1, you get 1/4. And when x is 2, you get 1. And notice I made 1 up here, not down here, because I want this graph to help me. So you don't want to concentrate everything in a little small section here. So I'm looking for this area right in here. So I'm going to go and make my rectangle. So here I go and say, that's my rectangle, and it's up and down, so I'm going to go, the width is dx, and the height is the bigger value minus the smaller value. Red minus purple. From where to where? From 0 to 2. Ooh, or be careful. Is it really from 0 to 2? What happens once you get to x equals 1? Your rectangle actually changes. Now it goes between green and purple, not red and purple. So we have 2 separate types of rectangles, which means we have to split this up into 2 definite integrals. I have to go from 0 to 1, and now the upper one is y equals x, and the lower one is y equals x squared over 4. And then I have to add to that. And now my upper one is y equals 1, and the lower one is the same parabola. So I have 2 to do here. Antiderivative, x squared over 2 minus x cubed over 12. On this side I get x minus x cubed over 12. Quite a bit of calculation to do here. So if I put in 1, I get 1/2 minus 1/12, which is 5/12. And this side I get 2 minus 8/12, or 2/3. And on this side I get 1 minus 1/12. So I get 4/3 minus 11/12, or I get another 5/12. So altogether I get 5/6 square units. And this is drawn a little bit more to scale. Notice 1 square unit would be this box right here. So that looks like about the same as that area. Now, as I was doing this problem, I was kind of saying, oh, I don't really want to do 2 integrals. I wonder if it would be possible to make the rectangles on their side. Look what would happen if I made the rectangle on the side. There, I'm always going between purple and red, no matter where I go. So I'd only have to do 1 rectangle. So I dropped down to here and said, what happened if I divided it up the other way? What if I called this C and this D, and I went from y0 and split it up to y sub n, and took a representative section here, the kth section, from yk minus 1 to y sub k, picked any value in between there and called it c sub k, and then took this distance here. Well, these are not functions of x. If I drew a vertical line here, every x value would have 2 different y values. So you don't have y as a function of x, but if I took a horizontal line, then I would have I would have a function of y. So every y value would only have 1 x value. So I'm thinking that maybe this red one right here is x equals f of y, and the green one is x equals g of y. And I can still make a rectangle. I can call the distance from here to here delta y sub k, and use that and make a little rectangle in that direction. And what is it going to be? It's going to be this. Now the bigger x value is the bigger to the right. So the red is going to be a bigger x value than the green. So I'm going to go f of c sub k minus g of c sub k. That's going to be one dimension of the rectangle. The other dimension is going to be delta y sub k. But we have n of them, so we better add them up from k equals 1 to n. But we don't want this error in here, so we take the limit as n approaches infinity. And what do we have? We have the exact same thing that we had up here, except now it's y instead of x. So really, this is just another definite integral. You're just going from c to d of f of y minus g of y dy. So I just justified to myself, and I hope to you, that I can go up and down or sideways. So let's just really quickly do this other one that we just did, but do it sideways. Make this with dy instead of dx. And I'm only going to go from y equals 0 to y equals 1 to add them up. Now, this is going to be the hardest part. What is the width of this rectangle? It's this x value minus this x value. So we have to have these solved in terms of x. Well, that one's going to be easy. X equals y. This one's going to be a little bit more of a challenge, but not too bad. X squared equals 4y. X equals plus or minus 2 square roots of y. And we're only looking at the positive side. The negative side would be the other side of this parabola. So I just know that this x value here is 2 times the square root of y. And that's the bigger x value. And the smaller x value over here is just x equals y. Y equals x is the same thing as x equals y. So what's the antiderivative? Y goes up to 3/2, and then I divide by 3/2 or multiply by 2/3, and then this is just y squared over 2, and you only go from 0 to 1. 0 gives you 0, 1 gives you 4/3 minus 1/2, or 8 minus 3, or 5/6, and we get the same answer we did the other way. I think you can see with a little less work. Okay, so let's proceed over to three more examples. Another one in the first quadrant. So I've only got the first quadrant graphed, bounded by y equals 8, x equals 1, a vertical line, and then y equals x cubed. So 0, 0, 1, 1, 2, 8. So that's what the cubic looks like in that part. And we see what we're trying to find the area of. Well, which way are we going to go? Let's try it both ways just for practice. Let's say we make our rectangle like this, up and down vertical. Then that's going to be dx as my width. My height is going to be this y value minus this y value. So the bigger y value is 8, and the little y value is x cubed. And you're going to go from x equals 1 to x equals 2. Let's just write them up this time instead of working them out. You've had a lot of practice on doing the fundamental theorem of calculus. If you did it the other way, now I'm going to make the rectangle on the side, dy. And y now is going to go from 1 up to 8. And here's where you have to, again, solve for x. This you get x equals y to the 1/3. And that would be the bigger x value than this x value, which is x equals 1. So the width of this rectangle is going to be this x value, y to the 1/3, minus this x value, 1. So either of these isn't too bad to do. They would give you the same answer. So I'd say that one was kind of up to your choice. Well, let's try one that's trigonometric. Only going from 0 to pi, so I've only graphed it from 0 to pi. The sine of x starts at 0. At pi over 2, it goes up to 1, and then it's back to pi. So there's the sine of x. The sine of 2x just gets compressed by a factor of 2. So it goes up to 1 at pi over 4, and then it's back down to 0. And now it would go negative in the second quadrant here, from pi over 2 to pi. So what area are we looking for? We're looking for this area in here and this area in here. Now, which way do we want to make our rectangle? You can solve for x, but then you get x to be the inverse sine of y. And I don't think you really want to take the antiderivative of that. In fact, I don't think you can as of yet. So, I think we're kind of forced to make our rectangle up and down dy. Red to purple, purple to red. So they're different rectangles. They're both between purple and red, but this one, the purple is the higher number, here the red is the higher. So you still have to break it up into 2. So you'd have to dig out your trigonometric memory. How do you set these two things equal to each other? You'd say the sine of x equal to be the sine of 2x to see where they intersect, but we know we can't really mix angles. So this is where we use the trigonometric identities. This is why you learn trigonometric identities, so you can do things like this. You can turn it into 2 sine of x, cosine of x. And now, if I put these on the same side of the equation, I can factor out a sine of x. And where are they going to intersect? Whenever this factor equals 0, which is at 0 and pi, where the sine equals 0, and where the cosine of x equals 1/2. That would make this factor 0. And that happens at pi over 3. So not at pi over 4 or pi over 2, but at pi over 3 is where this intersection point is. So now I know how to write my integrals. From 0 to pi over 3, and what's the high one up here? The high one is the sine of 2x at the beginning. And then you have to add to that the integral from pi over 3 to pi over here, and that's going to be the opposite way. That's the sine of x minus the sine of 2x. And it's kind of a fun one to work out. You get to practice your trigonometric antiderivatives, and you get to practice your automatics, but that's not really the purpose of this lecture right now. I just do one thing. What's the antiderivative of the sine of 2x? It's minus the cosine of 2x over 2. So you can see when you plug in pi over 3, you're going to have to know the cosine of 2 pi over 3. So you're going to have to dig out your trigonometric automatics. The answer turns out to be 2.5. And most of the area is going to come out of this integral over here. Okay, now on a lot of these, we could have picked the rectangles either way. This one really made sense to do it up and down. But it would be possible to do it the other way. But I thought I would give you one last one where you only have one choice. We're finding the area in the second quadrant between this parabola, which is a sideways parabola because x equals y squared, not y equals x squared, and the y-axis. So the y-axis is going to be part of our boundary. Now, if I factor this, I see when y is greater than 1, x is going to be positive. When y is less than 0, you get a negative times a negative or a positive. So it's positive down here and positive up here. But when y is between 0 and 1, you get a negative, positive times a negative or a negative. So we're negative between 0 and 1. What it's going to turn out to be is a sideways parabola like that. And we're only finding that area right in there. You really cannot make your rectangle up and down. To do that, I'd have to do all my calculations for y. And I don't have that in terms of y, and I can't algebraically solve it. No matter how good you are at algebra, you can't get y just in terms of x. So our only choice on that one is to make our rectangle on the side dy. We can only measure in the x direction because of this. So I'm going from y equals 0 to y equals 1. What's my bigger x value? My bigger x value is just x equals 0. And then what's my smaller x value? That's on the parabola. It's a negative value at this point. So it's y squared minus y. And then you just do your antiderivatives. The antiderivative of, well, I'll rewrite this. It's y minus y squared when you distribute that minus sign. And then you get y squared over 2 minus y cubed over 3. 0 again gives you 0. 1 gives you 1/2 minus 1/3, which is only 1/6 of a square unit. So that is a really small little area that comes into play there. So we've done about 5 different examples of some where you have to go one direction with your rectangle, some the other. That's pretty much how all areas are going to be done. So anyway, I hope that gives you some idea of a new application for integrals. We'll learn a lot more starting tomorrow. So thank you.